Hi, thank you for attending research seminar today. So I'm very happy to introduce today's speaker, Professor Soheil Kolouri at Vanderbilt University. Soheil runs the Machine Intelligence and Neural Technology MINT Lab, focusing on mathematical machine learning, geometric deep learning, and computational optimal transport. Before joining Vanderbilt University, Soheil was a research scientist and principal investigator at HRL Laboratories, Malibu, California, where he was the PI and co-PI on multiple DARPA programs. He obtained his PhD in biomedical engineering from Carnegie Mellon University. Okay, today, Soheil will talk about Wasserstein embedding in the deep learning era. Soheil, so please start your talk.
Hi, yeah, thank you for the nice introduction. It's a pleasure to be here today and talking with you guys about Wasserstein embeddings and some of our old and some of our new work on the topic. So let's start. I don't think I have to motivate machine learning. One of the reasons we are all here today is that machine learning has become a disruptive technology. And we know that currently we have like successful applications of machine learning in healthcare, for example, in diabetic retinopathy or augmented reality microscopes, or we have automated detection of breast cancer and so on. So it's a very hot topic to use machine learning in healthcare right now. But also we know that in transportation, for example, the self-driving cars are almost a reality. And thanks to computer vision and machine learning. And in energy systems, also we have a smart grids and Internet of Things and a lot of interesting applications of machine learning. But going beyond any specific application of machine learning and look at the core ideas in machine learning, we see that measuring dissimilarities between probability distributions is a common thread in a lot of different applications. Whether we talk about comparing one-dimensional histograms as shown here, or we talk about comparing two-dimensional, three-dimensional distributions like shapes and images, which commonly appear in the medical domain. Or we can be talking about higher dimensional distributions like distribution of images or distribution of text or sensor data. And in general, we can be talking about n-dimensional distributions where n is significantly larger than 3. So in a lot of these applications, we really require a reliable way of measuring dissimilarities between distributions. Okay. In two particular areas that measuring this dissimilarity becomes very important and crucial in machine learning are the density estimation as well as the deep generative modeling. Okay, where in this density estimation you have a parametric model Q with some parameters gamma that you would like to match your data P, and similarly in generative models you have a latent distribution that you sample and you would like to send that through a nonlinear function to obtain essentially a distribution that's parametric. The parameters depend on their generator, and you would like to match the generated distribution with the distribution of your data. So this matching is done through measuring a dissimilarity. Okay. So, but we already have many dissimilarity measures for probability distributions. Here, I include a short list of such dissimilarity measures. For instance, we have Minkowski distances, we have symmetric chi-square distances, Hellinger distance, Jensen-Shannon divergence. And in general, we can be talking about phi divergences for measuring dissimilarities between two distributions. These dissimilarities are great. They've been really well studied. But it's important to note that these dissimilarities are in nature bin-wise. So what we mean by bin-wise is that they are comparing distribution P with distribution Q at the same X, right? And so because they are bin-wise, here looking at these examples that I'm showing, the blue distribution and the green distribution and the orange distribution, if we look at the dissimilarity between blue and green, although these distributions are just like a slightly shifted version of each other, we're going to get a very high distance or very high dissimilarity. While if we measure the dissimilarity between the blue and orange, we are going to get a smaller dissimilarity. So while this might be acceptable for like certain applications, like if you have categorical distributions, like you have categorical data and we are talking about comparing histograms, in a lot of other applications, this actually is counterintuitive in the sense that blue and green should be closer or more similar to one another as opposed to the other way around. Okay, so let's look at an example, a simple example that's essentially highlights the importance of dissimilarity measures in machine learning. Consider two distributions, P and Q, where Q is simply a shifted version of distribution P. And if we plot the dissimilarity between P and Q as a function of the translation parameter tau, and plot this dissimilarity based on the different dissimilarity measures like Jensen-Shannon, Hellinger, L1, L2, and general phi divergences, we see that whenever the domains of the distributions are not overlaying, whenever the domains of the distributions are disjoint, we have a maximum value for these dissimilarities, okay, as you can see here. So this has two implications. The first implication is that if I have three distributions with disjoint domains, the dissimilarities that we have seen are going to tell us that, hey, these distributions are equidistant. So the pairwise distances between these distributions is exactly equal to one another, okay? While intuition tells us that if we have some geometry of our space, the blue and red distributions should be closer than the blue and green distribution. Okay, so that's implication one. And the implication two is that let's say we would like to match the P and Q distributions, and we would like to essentially optimize to find the translation parameter tau. And we would like to solve this optimization problem, argmin of tau, with respect to a dissimilarity between P and Q of tau. And then we would like to solve this with gradient descent, okay? And we had an unfortunate initialization where we initialize Q where there is disjoint, the domains are disjoint. Okay, in this case, our gradient is going to be 0, and we are not going to be essentially able to optimize this and find our parameter tau. Okay, but now if we look at the Wasserstein distance, we see that the Wasserstein distance essentially is providing a dissimilarity measure that's sensitive to the underlying geometry of the space, okay? And if we run our gradient descent, no matter where we have initialized, we're going to end up in the right global solution. Okay, so Wasserstein distances are generally good for capturing the underlying geometry of the space and are suitable for learning in a lot of different applications in machine learning. Okay, of course, I haven't told you what Wasserstein distances are, but I just want to give a very high level idea in the beginning that while all these other distances and dissimilarity measures or divergences that we talked about are bin-wise, the Wasserstein distances are going to compare distributions cross bins. Okay, so as opposed to doing just one bit at a time, we are going to compare them cross bins and measure how much we have to move one distribution to match it to the other distribution. Okay, so that's the high level idea. Now I'm going to actually start go from the motivation and start the talk. And here's the outline of my talk. There I have three sections. In the first section, I talk about optimal transport. I introduce what optimal transport is, what Wasserstein distances are, and so on. Then in the second part of the talk, I introduce the idea of Wasserstein embeddings. And in the last part of the talk, I talk about the sliced Wasserstein embeddings. And the main idea is to provide computationally efficient approaches for comparing large number of distributions with one another. So that's the common theme throughout the talk. Okay, so let's start. What is the optimal transport problem? As the title of this section implies, optimal transport, 18th century math for modern machine learning, optimal transport is an old problem. It's been around since 18th century, but its application in modern machine learning has become prominent, especially more recently. There has been a lot of interest in using the Wasserstein distances, which are rooted in the optimal transport in machine learning. So let's see what optimal transport is. So optimal transport goes back to the French mathematician Gaspard Monge in the 18th century. Monge studied the problem of how to transport the soil during the construction of a building of forts and roads with some military applications in mind. And they were interested in the minimal transportation expense to build these constructions. Abstractly, this problem is equivalent to finding the optimal matching or permutation that provides the cheapest transportation cost between a set of point xi's and a set of point yj's. Okay. So we can formulate the problem as measuring a distance between xi's and the source and the destination y of sigma i. Sigma i is telling us which y we are choosing. So essentially the permutation index. And we are trying to find the optimal permutation here that minimizes this expected transportation cost, where d is the transportation cost. Of course, this is a combinatorial optimization problem. It's not easy to solve. And it can be solved under very specific circumstances. Okay. But the good news is that later in the 20th century, Kantorovich, who was a Soviet economist, was studying the supply and demand problem, and he relaxed Monge's optimal matching problem, not being aware of Monge's formulation at the time, by introducing the idea of soft assignment. So in Kantorovich formulation, the mass particles, like the points xi's became mass particles with different amount of mass that could split and redistribute to go to different y's. Okay, so instead of having essentially a permutation sigma in the Monge formulation or a transport map, what Kantorovich proposed was a transportation plan that tells us how much of mass from location xi is being transported to location yj. Okay, so the gamma ij is telling us how much mass is being transported from xi to yj. Okay, and if we look at the transportation problem, the Kantorovich formulation of the transportation problem, we are still calculating the expected loss with respect the expected transportation cost with respect to this transportation plan that tells us how much mass we are moving between the particles. And we have a constraint that tells us that, hey, during this process, we don't want to create or destroy mass. Okay. But this Kantorovich formulation becomes a linear programming optimization. It's a convex optimization, although not strictly convex. And there are many good solvers we can use to find the solution for the linear programming, like simplex methods, interior point methods, and so on. Okay. So of course, I motivated the optimal transport in a discrete setting, which is not a conventional way of doing it. But I should mention that optimal transport is a versatile theory, and it's not limited to the discrete setting. Both Monge and Kantorovich formulations have their continuous counterparts. In particular, Monge's transport map becomes a push forward of a measure, here shown as F. And the problem of optimal mass transportation is essentially finding the optimal push forward from one measure to another measure. And optimality is in the sense of providing the minimum expected transportation cost. And similarly, Kantorovich formulation can also be formulated in its continuous form, where the transportation plan that we saw gamma in the previous slide becomes a joint probability measure, here shown as gamma, small gamma. But the problem doesn't change. It's still, we are trying to minimize the expected transportation cost. But one of the main appeals of optimal transport is that it provides a metric between distributions. And this metric is called the Wasserstein distance. Essentially, the Wasserstein distance between two distributions is equal to the minimum transportation cost between the two distributions. Okay, so the minimum amount of transportation we need to do to morph one distribution into another. Okay, here we see a Kantorovich formulation of optimal transport. So this is the Kantorovich formulation of the Wasserstein distance. But when the distributions are absolutely continuous and smooth, and we can essentially use Monge transport map and use the Monge formulation for calculating the optimal transport map. But let's see an example to kind of understand this a little better. Here, I am showing two face images. So I'm treating these images as two-dimensional probability distributions. So these images are normalized in a way that if we sum the intensity values, they're going to sum to 1. Okay. Then solving the optimal transport problem will give us the Wasserstein distance between these two distributions. But maybe more importantly, it provides us a transportation map that allows us to push one distribution into another distribution. And not only any transportation map, but the optimal transportation map, which is unique due to Bernier's theorem. Okay. When we say like morphing one distribution into another distribution in a differential form, we can have the determinant of the Jacobian of the transportation map F, or the push forward F, is going to times the Q evaluated at F, where Q is our target distribution, that's going to be equal to our source distribution P. Okay, for those of you who are familiar with image registration and image analysis, this term Q of F is essentially performing registration, while the determinant of the Jacobian is ensuring mass preservation. But at the same time, it's allowing us to perform modeling on texture, so to change the texture of the data. Okay. Now that we are equipped with the Wasserstein metric, we can talk about things like geodesics, or the shortest paths between two distributions. So if we think about the space of probability distributions here shown in yellow, and the shortest path between two distributions, P and Q, we can ask shortest in what sense? If we are talking about Euclidean distance, for example, of course, the shortest path is going to be the straight line connecting these two distributions. But in the Wasserstein case, the shortest path is going to be a curve in this space. Okay, and this curve is called the geodesic curve, and it is parameterized as the convex combination of the optimal transport map F star and the identity function X. So with essentially a convex combination of identity and the optimal transportation map, we can obtain distributions, and applying that to our source distribution P, we can obtain distributions on the geodesic on this line. Okay, so here is a visual explanation of what these geodesics are. On the left, you see the geodesic in the Euclidean with respect to the Euclidean distance, and on the right, you see the geodesic with respect to the Wasserstein distance. Here on the left, you see distribution Q. On the right, you see distribution P. And you see that when we are using the Euclidean distance, essentially connecting these with a line, what happens is that if we interpolate these two distributions and visualize the geodesic, the mass is being destroyed on one location and created in the other, or teleported in the other location, completely ignoring the underlying geometry of the space. Okay, here is in 1 dimension. Here you can see the same phenomena in 2 dimension, and for more complex distribution, which you see a face. And you see the same behavior that the middle point here, for example, you see 2 eyes and like a ghost effect of faces and so on. While when we go in the and calculate the Wasserstein geodesic, we have this transportation from one distribution to another distribution according to the geometry of the space. Okay, in 1 dimension, 2 dimension, and also for more complex distributions. Okay. So to summarize optimal transportation, optimal transport allows us to compare distributions in a geometrically faithful manner. Given 2 distributions, in this case, I have the state of Tennessee and the Vanderbilt's logo. What optimal transport gives us, and I forgot to say, and a transportation cost between samples. Optimal transport first gives us the correspondences between the samples from the distributions, okay, the optimal correspondences. Second, it provides a metric between these 2 distributions. This is not a sample metric, it's a metric for the distributions. So it lifts the ground metric to a metric between the 2 distributions. And it allows us to interpolate between different distributions and is useful for modeling, okay? So this is really the image that I have in mind when I think about optimal transportation. So far, I have told you that optimal transport is great, but then there is a caveat. And the caveat is that optimal transport is computationally expensive. So if we just think about solving the Kantorovich problem, this linear programming, in generally speaking, is super cubic. to solve. So it's n cubed log n to solve. There has been a lot of work in making this faster. One of the pioneering work was the Sinkhorn divergences or Sinkhorn distances by Kolouri, which essentially solves an entropy regularized version of this problem, and that makes it this not super cubic but still quadratic to solve. Okay, but then you lose accuracy in actually finding the optimal transportation map. So, but if we want to calculate pairwise Wasserstein distances between a set of m probability distributions, say we have probability measures mu1 through mu_m, and we have to calculate pairwise distances, pairwise Wasserstein distances, then we have to calculate m squared of these n cube log n, and that's going to be really expensive to calculate. And similarly, if you want to do gradient descent, for example, using optimal transport, in each step of our or gradient descent, we really need to solve this this supercubic problem. Okay, and I'm talking like very generically. Of course, there are other ways to get around this. For example, using the dual and not solving the whole thing. But that aside, the problem remains that optimal transport is computationally expensive. Okay, so now I can start talking about the first part, essentially the second part of the talk, which tells us what can we do to reduce these m squared computations of optimal transport to simply m calculations of optimal transport problems, and still allow us to do modeling on m distributions. Okay. This is the idea of linear optimal transport or Wasserstein embeddings, and this was work done jointly with Gustavo Rode and Dejan Slepčev at Carnegie Mellon. Okay, so I'm going to motivate the concept of Wasserstein embedding through biomedical application. We were studying the predictive modeling of cancer in the liver tissue by considering the chromatin content in the cell nuclei. Okay, so we had whole slides of pathology images from which we had segmented nuclei, and each segmented nuclei was showing the distribution of the chromatin content in the nucleus. And we treated each image as a two-dimensional distributions. And here in this example, we had two groups of patients, one with malignant cancer and the other one was with a benign tumor. Okay, and the question that we had to answer was, are there differences between these two groups? And of course, that's any machine learner or a statistician's favorite question, because we know a lot of different ways to find statistical significant ways if such discrimination exists between these two groups. That's essentially the easy part of the question. But maybe a little bit more challenging, we didn't just want to say if there are differences, but we wanted to also say like what are the differences between these two groups. And so here I'm showing what we did, and I'm going to explain what that is. And this was a PNAS publication in 2014, so ancient. But the idea is I'm going to communicate the idea now. So we were inspired by the research in the field of computational anatomy, where folks are interested in analyzing shapes. Okay, and a common idea there is to fix a reference or a template shape, and then calculate and register each of the shapes into this each of their shapes into the reference shape. Okay, and then instead of analyzing the shapes directly, they perform a statistical analysis on the registration fields, these vector fields that are solving the registration problem for us. Okay, so this is a great idea because it only requires m calculation of the registration. So that's the good news. The bad news is that first, the registration is not unique. Solving the registration problem is not a convex problem often, and the registration map is not guaranteed to be unique. And second, and maybe more importantly, this framework is designed for shapes. It doesn't allow us to model textures. Okay. But of course, we were familiar with optimal transport at the time, and we knew that optimal transport first gives us unique transportation maps. And also, it allows us to not only model shapes, but also model texture variations. Okay, so then this is the core idea behind Wasserstein embeddings. that for a fixed reference, you can calculate the optimal transport map that pushes your input measure into your reference measure. And we can think about that as a forward embedding. So for an image, we are going to get a unique transportation map. And then this embedding is invertible in the sense that we can use the transportation map and calculate the pullback with respect to our reference here shown as I0 and recover our input image. Okay, so that's the really high level idea of Wasserstein embedding. So then we can show that this Wasserstein embedding actually provides some interesting geometric concepts, in the sense that if we calculate the Euclidean distance in the embedding space, the Euclidean distance is going to approximate the Wasserstein distance between the distributions in the original space. Okay, so calculating the Euclidean distance on these transportation maps is going to approximate the Wasserstein distance on the input distributions. And then the idea is to transform our distributions into this tangent space, into this embedding, where each distribution becomes a transportation map, and then perform statistical analysis on the transportation maps, and then use the inverse or the pullback to visualize the variations or visualize the changes on the distributions in the original space. Okay, so, but of course I said that this Euclidean distance in the embedding space is an approximation of the Wasserstein distance. And I have to provide a sense of how good of an approximation it is. And thankfully, Caroline Mussmuller and Alex Cloninger had a fantastic paper recently that they studied this embedding very closely, and they quantified the approximation error for this embedding. So in short, what they showed was that two measures mu I and mu j, if they are push forwards of a measure mu, under shifts and scalings, then this embedding is isometric, in the sense that the Euclidean distance is going to be exactly equal to the Wasserstein distance in the original space. But maybe more importantly, this embedding becomes near isometric if the two measures mu I and mu j are essentially generated from the reference distribution by a push forward with respect to an epsilon tube around the set of shifts and scalings. Okay, so there is a question here. I'm still trying to understand page 17 and 18. Does transport to reference I0 mean that the output of the encoding phase is approximately equal to the reference? No. So we have two distributions, distribution I, or two measures. Here I'm using densities. So we have two distribution II and the reference distribution I0. Okay. So if we calculate the optimal transport map between these two distributions, this is going to give us a push forward of one measure into the other measure, right? So we have a push forward, which is a vector field, in this case, a two-dimensional vector field, that allows us to push transport mass from one distribution into the other distribution. Okay, so that's our embedding. That vector field is our embedding. Now, because we have this vector field, we can apply it in a forward manner to calculate the push forward going from our input to our reference. But we can also apply the inverse of it, right, and do the pullback. And if we do the pullback, we are essentially transporting mass from the reference back to the input distribution. So what the embedding is that it's a transportation map. Where does the reference distribution come from? That's a very good question. The reference, we will actually talk about like what this reference should be. A good choice for this reference is the Fréchet mean of your data set, okay, all your distributions. Or one distribution in your data set that's close to everything else in the sense of the Wasserstein distance. But actually, Mussmuller and Cloninger's results tell us something interesting, that like so long as your reference can be transformed to all your distributions closely as a shift and scaling and a little bit of something else. So with some push forward that's within an epsilon tube around the set of shifts and scalings, then your embedding is going to be very close to an isometric. It's nearly isometric embedding. Okay. So then let's see some examples to clarify the ideas a little bit further. Say we have a fixed reference, and here we have our distributions I, and ij, and we calculate our optimal transport. We get our transportation maps fi and fj, right? So this is our embedded distributions now. And say we calculate the convex combination of our embedded points, and also we calculate the convex combination of our input distributions. Okay, so when we look at the convex combination of our input distributions, we had this Euclidean geodesic. Okay, and we saw that the ghosting effect happens. But when we do this convex combination in the the embedding space and then calculate the inverse of this F alpha, we get something that's very close to the Wasserstein geodesic. It's not the Wasserstein geodesic; it's an approximation of the Wasserstein geodesic, but it closely resembles the Wasserstein geodesic. Okay. Here is a toy example showcasing the capabilities of such embeddings. Say what we are looking at, the data set is a data set of two-dimensional distributions. These are ring distributions. So we have samples from ring distributions that are translated and scaled. And then, oops, sorry. And then we have different number of samples per distribution. So they can have like one can have 100, the other can have 150, something else. And then what we do is we select a reference. And in this case, our reference is actually selected arbitrarily. This is like a normal distribution that we have selected as our reference. And then we calculate the approximate Monge map. This approximate Monge map is the vector field that I talked about that pushes our reference measure to the input distributions. And then if we calculate the mean of the embedded distributions and visualize and apply that mean to a reference measure, we see that the mean of the data set is recovered as a ring, which is really, really exciting, right? And then we can also calculate geodesics in the embedding space from the reference to any point or between different distributions. And you can see still that transportation is happening. Okay, so what is the relationship between Wasserstein embedding and Wasserstein barycenter? Wasserstein barycenter is trying to find a distribution that minimizes the Wasserstein distance between many distributions and the distribution that you're trying to optimize. So Wasserstein barycenter is the problem is find a distribution that has the minimum Wasserstein to every single distribution in your data set. Okay, so here we are really not in the business of finding a new distribution. You can use the Wasserstein barycenter as the reference measure. That's absolutely fine. That's actually a good idea. But here, what we are doing is completely different. Here we are mapping a distribution into a different space. So let's think about like transformations, like Fourier transform, wavelet transform. These transformations, what do they do? We have a signal in our input, and we send them to a transformation space, and we apply some sort of analysis in this transformation space, and they're usually invertible, right? Fourier and wavelet are invertible transformations, so we can always go back to our signal space. Here, what we are doing is very much along the same base. We can think about it as a transformation. We have a transformation into an embedding, and this transformation is invertible. And also this transformation is a non-linear transformation as opposed to a linear transformation. So very different concepts. Wasserstein barycenter is completely different from this Wasserstein embedding idea that we're talking about right now. Okay. So I may actually go a little over time because I'm answering the questions. I hope that that's okay. You can tell me otherwise. So let's go back to the chromatin distribution in cell nuclei, the example that we saw. We have the two groups, and here I'm just visualizing the two groups as distributions on in the space of the distributions. Then we perform or embedding. This embedding is taking a distribution, sending it into essentially the transportation maps. And then we can perform here parametric learning on the training set. In this case, let's say we apply linear discriminant analysis, simply LDA. And of course, there we can visualize projection of the data onto the LDA's subspace, in this case, just the one-dimensional subspace. And we get that the two groups are different from each other. But then because we are able to invert this mapping back to the space of the distributions, we are able to visualize variation along this discriminant direction. And when we do that, we recover this nice visualization that's telling us that the difference between the two two groups of nuclei is a migration of chromatin from the periphery of the nuclei image to the center of it. Okay, so now we not only have a way of measuring discrimination or statistically significant discriminant direction, but we can also visualize the variations as well. Okay, but besides discriminative analysis, we can perform exploratory analysis of the data, say by applying principal component analysis (PCA) in the embedding space. Sorry. And then visualize and then inverting this embedding and visualizing the principal components in the original space. And you see like very nice transition of like the first component, and first component is telling us the size difference is the biggest variation, and so on. And the fourth component is actually the discriminant variation that we see. Okay. But maybe more interestingly, we showed that if we capture the if we calculate the percentage variations captured by a number of principal components, so here the x-axis is the number of eigenvectors or number of principal components used, and the y-axis is showing the percentage variations captured, we see that performing PCA in this embedding space allows us to capture much more variations of our data with much fewer number of parameters. Okay, so it gives us a little bit more of modeling power as well. This is in comparison with if we do it in the image space or if we do it in radon and ridgelet spaces. Okay, so this embedding actually provides like a better way of modeling your distributions. So knowing that we can perform this Wasserstein embedding for two-dimensional distributions, then we said, can we extend this to three-dimensional distributions? And of course, like brain images are a good example of three-dimensional distributions. Here we have MRI images, three-dimensional MRI images of two different classes of patients or people. Class one is persons with low fitness index. Class two is persons with high fitness index. So of course we go through the common pre-processing like a skull stripping and pre-processing for of this volumetric data, and minor affine registration. And then we have a reference, and this reference is simply the atlas used for registration in the field. And then we calculate the transportation maps from each of the individual brains to the reference, and we get these three-dimensional vector fields, perform more statistical analysis in that space, and then invert or analysis back into the image space. And I'm not a neuroscientist, but even I can see that there are visual differences between least fit person and the most fit person. Specifically, if you look at the ventricles. Right. Okay. So let's see what we have talked about so far. So far we have talked about why we need better probability distances or dissimilarities. Then we talked about optimal transport and Wasserstein distance is a suitable way of measuring dissimilarity measures, but we said that they're expensive, and if we want to do pairwise analysis, they become too cumbersome. And then we talked about Wasserstein embedding, which reduced our computation from m squared from pairwise to calculating only optimal transport from or m distributions to a reference distribution, so m calculations. And we have seen the applications for two-dimensional and three-dimensional distributions so far. Okay. Of course, the natural question is, can we extend this to n-dimensional distributions and look at other types of distributions? Okay. This brings us to work that we recently did. This was presented in iClear 2021 earlier this year. It's called the Wasserstein Embedding for Graph Learning. And this work was done with my wonderful colleagues, Navid at UPenn, Gustavo at UVA, and Heiko Hoffman at HR Laboratories. So let me briefly motivate the problem and tell you why we actually went this way. So we had data sets that didn't live on regular grids. So we know that signals, images, and videos live on regular grids, right? But we know that there are a lot of other types of data that live on graph structured data, right? They're graph structured data. They live on irregular data structures, okay? And we wanted to do learning from such data. And of course, like the common approaches out there right now are graph neural networks and, for example, graph kernels for performing machine learning on graphs. Okay, but let me tell you a very high level core idea in the graph neural network approaches. So the graph neural network approaches have this common two steps. Okay, the first step is, given a graph, you do some sort of a local aggregation of your node features and embed each node in a vector space, in a d-dimensional vector space. This is called the node embedding process. Okay, so now each graph is going to be represented as a collection of points in a d-dimensional space. Okay, and you would like to perform machine learning on this. You would like to solve a classification or regression problem. Okay, but of course the graphs can have different number of nodes, and you can have you can't really have a fixed dimensional representation for your graph if you want to do like classic machine learning down the road, right? So then the common idea here is to use a global pooling. For example, a very common one is an average pool, or there are other ones like max pool, and this is a global pool. And so essentially simply take the average of all your node embeddings and represent your graph as that average point. Okay. Then the idea is then, okay, you can send this the downstream applications like for classification, for regression, and whatnot. Okay, so the very high level idea consists of node embedding and then a way of extracting a fixed dimensional representation from this node embedding and then performing downstream tasks. Okay, so when we were studying this, we immediately noticed that, okay, using the mean as a pooling is essentially telling us that we have a distribution and we are relying on the first moment of that distribution to represent that entire distribution. And we were starting to look into like, can we do something else? Can we use optimal transport to compare these distributions? And apparently at the same time, like other teams were also looking at this idea and they beat us to it. Toninelli et al. Like had a wonderful paper in NeurIPS 2019, and they said, okay, yes, we can measure the Wasserstein distance between these node embeddings, between these empirical distributions in our embedding space, node embedding space. Okay, and if we calculate the Wasserstein distance between these two, we can define a kernel based on the Wasserstein distance and then use kernel methods to do this. Of course, you need to calculate pairwise similarities using this technique between your graphs. You need to still calculate n² number of optimal transportation problems. But since we had Wasserstein embedding, we thought that this is actually a perfect example that we can use. And here we have d-dimensional distributions. We simply embed these d-dimensional distributions using our Wasserstein embedding. And the Wasserstein embedding is going to give us a fixed dimensional representation for our distributions. And then we can perform downstream tasks. Okay, so here is a visual depiction of what's going on. We have our embedding, we have a reference distribution, and then we calculate the optimal transport from reference distribution to any of the node embeddings, here shown as these vector fields. And then we use those vector fields as a fixed dimensional representation. So essentially we concatenate these vectors and we have a fixed dimensional representation for each input graph. And as I mentioned, for M graphs, our approach only requires M calculation of Wasserstein distance as opposed to the m² of Toninelli et al. Okay, so this is a very simple idea, right? And we showed that actually this simple idea led to state of the art at the time, and leads to a very competitive performance now. There has been some recent work that beat us. But so here I'm showing the results on the OGB mol HIV benchmark data set. So this is a molecule classification data set. So you would like to essentially classify whether a molecule can inhibit the HIV virus or not. And using this Wasserstein embedding idea, we were able to provide a state of the art at a time. And also other results on other benchmark graph classification data sets using the TU data set. And we showed that we consistently perform really well for this data set as well. But maybe a little more importantly, and we not only perform really well, but we have very cheap calculation as well. So computational cost for this approach is very low compared to the graph neural networks and also the work from Toninelli et al., which is called the Wasserstein Wiesfeld-Lemon, WWL. Okay. And this essentially concludes the extension of the Wasserstein embedding to the n-dimensional distributions, where these n-dimensional distributions are representations of graphs. Okay, so next I'm going to focus on the last part of the talk, which is talking about a sliced Wasserstein embedding. And so far what we saw is that if we simply calculate the pairwise optimal transport problem between our distributions, we are going to have m squared n cubed log n calculation, and that was really bad. We said using the idea of Wasserstein embedding, we can reduce this computational complexity to m n cubed log n. But then, independent of reduction on m, we can reduce the calculation on the optimal transport. So instead of calculating n cubed log n, we can calculate sliced Wasserstein distances, which I'm going to tell you what sliced Wasserstein distances are. And then that's going to reduce our complexity to kn log n, where k is the number of slices used to calculate the sliced Wasserstein distances. I'm going to mention what that is. And then if you combine this idea of, there's a question, will different reference distribution affect the performance, or the difference is trivial? So for the Wasserstein embedding, it really depends on the application, but there is a significant effect on how you're choosing your reference. The reason is exactly the results of Mussmuller and Cloninger, right? So what they say is that if your measure is off, if your measure is your reference measure is completely far away from your other measures in your data set, then your embedding is not going to be a good approximation of the Wasserstein embedding. So you will still get an embedding, but that embedding is far away from near isometric embedding that you would like to have, and that can have severe consequences on the performance of your method. Okay, I hope that answers the question. So yeah, in like what I mentioned is that we can go to the sliced Wasserstein distance and have kn log n, and if we use the sliced Wasserstein embedding, then we are going to essentially have km and log n calculations, which is the best you can do for comparing the distributions. Okay, so I mentioned that solving the optimal transport problem at each, solving the optimal transport problem is an expensive operation to solve. But what I didn't tell you is that in one dimension, it's actually quite easy. You don't even need to solve an optimization. There is a closed form solution for optimal transport problem. And the Wasserstein distance can be simply calculated as the Minkowski distance between the quantile functions of your distributions, where the quantile functions are the inverse of the cumulative distribution functions. Okay, so in one dimension, things are easy. Actually, you can calculate the Wasserstein distance in n log n. Okay, but of course, one-dimensional distributions are not as exciting or as interesting to us. We would like to be able to extend this to higher dimensions, and this is exactly where the ideas from integral geometry come to our rescue. So From integral geometry, and it's in particular in computational tomography, this is a prevalent idea used in computational tomography. The idea is from Johann Radon, and if you're familiar with Radon transform, that's exactly what we're talking about here. And the idea is that you can always slice a d-dimensional distribution into a family of one-dimensional distributions, and this family of one-dimensional distributions are going to essentially preserve all the information about your d-dimensional distribution. So you can recover your d-dimensional distribution from this set of one-dimensional slices. So here I'm showing examples of a two-dimensional distribution and sample slices. So one slice is a one-dimensional distribution, another slice, and so on. So I use the term slices. I never defined what a slice is. Actually, the slice is integration over hyperplanes of the dimensional distribution. So these hyperplanes are parameterized with a unit vector shown as theta. And what we're doing to slice a high dimensional distribution is to integrate the distribution along the hyperplanes orthogonal to this parameter theta. Okay. And here we are showing the slices. If you just simply concatenate all the slices and obtain your Radon transform, then you can use the inverse of the Radon transform and recover your d-dimensional distribution from the one-dimensional slices. Okay, so then we can combine these two ideas of the cheap calculation of one-dimensional Wasserstein distance and this idea of a slicing, and talk about the idea of a sliced Wasserstein distances. So a sliced Wasserstein distance essentially tells us that let's slice two d-dimensional distributions into one-dimensional distributions and measure the Wasserstein distance between their corresponding slices or corresponding one-dimensional distributions. And so this is going to give you one Wasserstein distance between the two distributions, and you need to do this for all possible slices. So let's calculate the expected value of the Wasserstein distance calculated on all possible slices that we can have. Okay, so is this a true metric? The answer is yes, this is a true metric. Slice Wasserstein distance is a true distance. And actually it is topologically equivalent to the Wasserstein distance. And we had a NeurIPS 2020 paper with some folks in Paris Telecom and INRIA that we showed that there are statistical relationships as well between the slice Wasserstein distance and the Wasserstein distance. Okay, so I told you that we need to calculate the expected Wasserstein distance over all possible slices, but this means that we have to have an infinite, this integration is over an infinite set essentially, right? We have infinite number of slices and we can't calculate this. So Monte Carlo integration comes to a rescue, and we essentially calculate a Monte Carlo approximation of this integral on k slices. So we can write this approximation as sliced Wasserstein of a subscript k, showing that it's calculated on only k slices. So how does this work? Given two distributions, we can essentially slice these distributions on k different processors. So each processor is going to slice this distribution with respect to a random parameter theta, and then we calculate the Wasserstein, and this calculation is simply n log n. And then after we have these Wasserstein distances, we simply calculate the average of all of them to calculate the sliced Wasserstein distance. Okay, and the overall computational cost here is knd plus kn log n. So knd plus log n, where the n log n comes for calculation of the one-dimensional Wasserstein distance, and this knd comes from the slicing operation. Okay, so this seems like a very nice idea and a computationally fast idea. I just want to mention in a parenthesis that I talked about Radon transform. I talked about the slicing as integration over hyperplanes, but we can actually generalize this idea, and this brings us to the generalized Radon transform, and we can define a slices as integration over hypersurfaces as opposed to hyperplanes. And so we had a NeurIPS 2020 paper that shows us that you can actually define a distance, a new kind of distance called generalized slice Wasserstein distance, by simply generalizing this notion of a slicing from integration over hyperplanes to integration over hypersurfaces, which opens the door to a lot of interesting questions. Okay, so getting back to the flow, so here I just want to mention that this is a two-dimensional extension of the one-dimensional example that we saw earlier in the talk, where we had two distributions P and Q, and one was a shifted version of the other. And we wanted to find essentially the landscape or the dissimilarity measures based on so the value of the dissimilarity between these two distributions based on different measures of dissimilarity. Here, the same thing that we saw before, when the domains are disjoint, we get a maximum value, and then that's for phi divergence types and Minkowski and so on. For Wasserstein, we saw that there was a nice, nice geometrically meaningful loss landscape. And we see that the sliced Wasserstein provides something that's very similar to the Wasserstein distance. And so that's why we say it's topologically equal. They both provide big convergence of the measures. Okay, so now that we know what the sliced Wasserstein is, then it's like a small leap to generate the notion of Wasserstein embedding. So we know what a Wasserstein embedding is, we know what the sliced Wasserstein distances are, then the idea of a sliced Wasserstein embedding is combining these two. So the idea is, if you have a distribution, an input distribution here shown as Pi, and you have a reference distribution here shown as P0, we are going to slice this distribution on L different slices or K different slices. I'm using K and L interchangeably, sorry about that. And then we have one-dimensional distributions, and we can calculate the Wasserstein embedding between these one-dimensional distributions. And remember that the Wasserstein embedding was simply the Monge map, right, between the distributions. So this is going to give us one Monge map, another Monge map, and another Monge map. So we are going to have L Monge maps, and we can simply concatenate these L Monge maps and treat that as sliced Wasserstein embedding. Okay, so that's what our embedding is, and we can show that very much similar to the Wasserstein embedding. Here we have that the Euclidean distance on this sliced Wasserstein embedding is going to approximate the sliced Wasserstein distance, but this approximation is not due to this approximation here is due to the Monte Carlo integration. So if we had infinite number of slices, this is an isometric embedding, just as a side note. Okay. Okay. So, and for the remainder of the talk, hopefully I'll be able to convey that this idea of a sliced Wasserstein embedding is going to be easily integrated into modern neural network architectures as a pooling layer. And that's our NeurIPS 2021 paper that we are going to present in the upcoming conference. Okay, so for the sake of time, I'm going to skip over this. It's just showing that you can actually calculate the geodesics very much similar to what we saw before with respect to a sliced Wasserstein embedding as well. Okay, so very briefly, we just recently published a paper on classification based on a sliced using a sliced Wasserstein embedding. And so what we did was we said, if we have different distributions and different groups that we would like to classify, here the data set is a hand gesture data set. Each two-dimensional image is treated as a two-dimensional probability distribution function. And we can calculate the sliced Wasserstein embedding, which is the transport maps of slices. And then if we perform a subspace modeling for different classes in our sliced Wasserstein embedding, and for our classification, if we use a nearest subspace classification, then this provides a very powerful classifier, especially in the low data regime. So when we don't have many data points, this becomes a very powerful classifier. And we showed some results comparing our classification in the sliced Wasserstein embedding based on this idea of subspace modeling with training neural networks. So x-axis on these plots shows the number of training samples used to train the neural network, as well as train our sliced Wasserstein embedding. And we see that whenever we are in the very low data regime, like fewer than 10 samples, of course, our neural networks are failing miserably because they are data hungry approaches, but the sliced Wasserstein embedding provides really competitive accuracies. And like this is for 3 different data sets that we observe the same behavior. Of course, when you have a lot of data points, neural networks are going to start outperforming our sliced Wasserstein embedding approach. But just wanted to mention that this is a powerful benchmark for a low data regime classification. Okay. So the last stretch, and I try to go over this very fast. I'm already over time. The idea of a sliced Wasserstein embedding can also be thought as a set to vector operator. So for those of you who are like interested in maybe classifying or performing machine learning on set structured data, this is the sliced Wasserstein embedding idea can be used. And so this part of the work is done in collaboration again with my collaborator Navid, Heiko, and Joe at HR Laboratories. Navid is currently at UPenn, and my PhD students Eva and Brian. Okay, so here this figure is essentially just the sliced Wasserstein embedding. So we have an input set. So we have a set xi. We can treat this set as an empirical distribution. And we have a reference set. This is another empirical distribution. We generate random samples from our unit sphere. These are our slices. We slice these input set and the reference set, and we calculate the approximate Monge map. And then we simply combine these or concatenate these approximate Monge maps and generate a fixed dimensional vector to represent our set. And so for L slices and M number of samples in a reference set, this embedding is going to be an LM dimensional embedding. Okay. So now we have an approach that can take a set and generate a fixed dimensional vector from it. Then we tested the performance of our approach on set structured data. So what is a set structured data? For example, point cloud data sets are set structured data. Okay, because we have a set of points, set of 2 or 2, in this case, 3-dimensional points. And we would like to, based on that set, we would like to say what type of object are we looking at? For example, this is an airplane. Okay, so classifying point cloud data is something that we can do based on this idea of a sliced Wasserstein embedding. I'm going to skip over this for the sake of time, but then very much similar to Wasserstein embedding for graphs, here we can input our sets and then have a backbone. For example, this backbone is like in any neural network approaches applied to sets, there is essentially a permutation equivariant backbone that's applied to sets. And then that's followed by a permutation invariant function. That permutation invariant function is a generic pooling, like we saw, for example, average pool. But here we can replace this permutation invariant pooling with or a sliced Wasserstein embedding. Okay, and we can start looking at the performance of the methods based on combining a sliced Wasserstein embedding as a pooling in a neural network. And what's interesting is because we are in a deep learning regime, everything can be trained end to end. And when I say everything, here we can actually optimize over the reference measure. So the question of the choice of the reference measure shows up here again, but we can optimize the reference measure in an end-to-end manner along the way that we are optimizing our deep neural network. And also we can optimize our slices. So before we said we use the Monte Carlo approximation, we use random slices. Here in a neural network setting, we can actually optimize over these slices to maximize, for example, our classification accuracy on our set classification. And so these are the results on the ModelNet dataset, which has 40 classes of different objects. They have point cloud data from 40 classes. So what I would like to point out here, and the most important message here is The results that I'm showing in this table are showing the results of using different backbones. So if you apply a multi-layer perceptron versus if you apply a transformer network on your point cloud data. And then these are the permutation equivariant part. And then followed by a permutation invariant part, which is if you use a global average pooling or if you use the slice Wasserstein embedding. Okay, and of course for a slice Wasserstein embedding, you can choose different number of slices, and we are reporting our results for a slice equal 1 to a slice equal 1024. Okay, so the important message here is that when the backbone is simple, like a multi-layer perceptron, global average pooling is going to perform really bad, right? While the slice Wasserstein embedding provides a really good answer here. Of course, when we go to the transformers and we increase the complexity of our backbone, a global average pooling starts shining. It works really nice, but at the cost of making the backbone very complex. But while by making that complex backbone, we only get a minor improvement over using this slice Wasserstein embedding. So the results that we are getting with the slice Wasserstein embedding as pooling, using a very simple backbone, a multi-layer perceptron backbone, is on par with using gap with transformer backbones. So that's the powerful message or the powerful results that we got. And again, this is going to be presented in NeurIPS 2021. Okay, so I talked too much. Just what to remember from this talk is why probability distributions and the similarity between probability distributions are important. Why optimal transport is an interesting and nice geometrically meaningful idea. What are Wasserstein embeddings? How can they help us and how can they improve computation? And then we talked about the idea of the slice Wasserstein distances and the computational benefit we can get from them. And then finally, we talked about the slice Wasserstein embeddings, which also could be integrated into our deep neural networks. And finally, I would like to thank all my collaborators, without whom this work wouldn't have been possible. And also, if you're interested in any of the papers or codes, please visit our lab's website, MintLab. Thank you. And I see that there is a question here. So in the framework of slice Wasserstein embedding, is there some way to recover the Monge map for the original space? And if it could be recovered, would it be useful for interpretability, which I think we saw in some examples in the first work? Fantastic question. Okay, so because okay, if your input distributions, first of all, I'm thinking that the question is asking about the empirical distributions. Okay, if you have empirical distributions and we are slicing these, and these empirical distributions have different number of samples, it's really impossible to recover with this framework. You only recover an approximated empirical distribution, right? So you can go to the embedding and you can recover something, and that recovery is going to be only an approximation. And what I mean by an approximation is your input distribution had n points, n samples, but the recovered distribution is going to have m samples. Where m is the number of samples in your reference measure. Okay, so this is when you have empirical distributions. If you have continual distributions, like you're dealing with two-dimensional images, then this is an invertible process. Of course, again, a pseudo-invertible process, because Radon's results hold if you have infinite. The invertibility of Radon transform is only possible when you have infinite number of slices. And here we are using a Monte Carlo approximation with only k or l number of slices. And that also introduces some error. But you can, for both cases, you can recover something that's very close to your input distributions and still use it for explainability. Okay, so I hope that that answers the question. Page 49 here. In this example, is it possible to visualize the learned slicers? Yes, it is absolutely possible to learn to visualize the learned slicers. But what I'm not sure is there are a lot of things that we can visualize here for better understanding the approach. So these slices are being applied to the output of the embedding. sorry, these slicers are being applied to the output of your backbone. Okay, so you have a backbone that's applied to each of your points, the samples in your point cloud, and then let's say from 3 dimensions you have gone to a d-dimensional space, to a 16-dimensional space, or to a 128-dimensional space, and these slices are calculated in that space, in the 128-dimensional space. And I'm not sure like how beneficial it would be to look at the slices there, but certainly you can look at them. Maybe something that's a little bit more interesting is, can we visualize the reference, the optimized reference measure? And we can do that. And actually what we saw is that our optimal reference measure is starting to look like a cube, because our samples live in a cube. We normalize our samples to live in a cube, and we start from a normal distribution as a reference, and we optimize it, and we see almost a uniform sampling on a cube for this specific data set. So there is something there, I would say.
Okay. Yeah. Oh, there's one question, please. So if you have a question, please, you can ask directly, or you can just type into the chat box.
May I ask a question?
Yes, please.
Very impressive talk. I believe this will be the future of the machine learning, I think. And my question is that, how many data do you need to find a reasonable transform map?
Oh, I see. So okay, that's a really good question. Okay, so that's if I'm understanding it correctly, this actually is kind of an orthogonal question to the talk, in the sense that how many samples from a distribution do we need to be able to approximate the optimal transport map accurately? So the question is regarding the sample complexity of the Wasserstein distance, right?
That's right.
Right. So actually, we know that sample complexity of the Wasserstein distance is not good in higher dimensions.
Right. In the case of the high dimensional data, the sample usually sample is very small compared with the unknown parameters. I mean, unknown parameters value. Right. So that is the problem. I think to estimate the optimal transport map, do you need any regularization factor or something? How do you impose some condition? I mean, this transportation map should be regular. It shouldn't have any singularity in it, right?
Right. Yes, so absolutely. Okay. Go ahead.
Please. So what kind of modeling for this map do you use?
Okay, so fantastic question. Thank you for bringing this up. Right, like, this is really an interesting question. Okay, so first, like, this question specifically applies to the Wasserstein embedding and Wasserstein part of the talk. Because the sample complexity of the Wasserstein distance is really bad for it scales exponentially with d, right? So you need exponentially many more samples as a function of your dimension. This is not true for the sliced Wasserstein, right? So a sliced Wasserstein sample complexity I'm not 100% sure, like, if it is d, it's not exponential with respect to d. That I know. I'm kind of like shooting blank right now. But actually, in our NORIPS 2020 paper, we show that the sample complexity of a sliced Wasserstein distance is not exponential. So that's the benefit that you get using the sliced Wasserstein distances. But okay, so that aside, going back to the Wasserstein case, I mean, the regularities, we actually never calculate the Monge map itself. We are always calculating simply a vector field that's an approximation of the Monge map in the d-dimensional space. And yeah, I have to really think about it. But there are, I completely agree that like you definitely need regularizers. Like for example, we know that Monge map is like curl-free vector field, right? That's one. It's the gradient of a convex potential. And so things like that, absolutely. And some smoothness, I believe there are like a smoothness Caffarelli's result, if I'm not wrong. But there are smoothness properties that we can impose too. But honestly, I haven't thought much about that. But yes, you need to regularize for sure to be able to recover an actual Monge map, where in everything that I've talked, whenever we are actually calculating the Monge map, we are in 2-dimension or 3-dimension on images. And in higher dimensions, we are usually just having a very crude approximation, vector field approximation of the entire Monge map. Yeah.
Right. So you are talking about some sliced, non-linear sliced
yes.
Wasserstein embedding. How do you choose this hyper manifold?
Oh, that's a fascinating question too. So that's a fascinating question. So just briefly, if I go back to the radon transform formulation, this I think helps the conversation. So the radon transform, we saw that we can write a slice. It's essentially an integration over this hyperplane. So this x inner product theta is this delta is a Dirac function. This delta t minus x inner product theta is implying the integration over these hyperplanes, and this t are essentially this is telling us that we are integrating over the level sets of this function, right? X inner product theta, and x inner product theta, the level sets of x inner product theta are these hyper planes. Okay, and now when we go to the generalized case, all we have done here is to replace that x inner product theta with a nonlinear function, right? We have now a generic nonlinear function, but we are still talking about the level set integration over the level sets of this nonlinear function. Okay, so now can we choose any nonlinear function there? And the answer is no. We actually in this Norix 2020 paper, it's called Generalized Wasserstein Distances. We show that there are 4 necessary conditions. They are not sufficient, but 4 necessary conditions on this G. And just to put it in a nutshell, this G needs to be smooth both with respect to x and theta. So jointly smooth with respect to x and theta. Okay, that's essentially the essence of the property that we need on this G. So there has been a lot of studies on generalized radon transform in the field of tomography. So if you think about acoustic tomography, the wave fronts are actually spherical, right? So this spherical wave fronts that I'm showing, this is actually, you can show that if you use a spherical wave, like if your like level sets are this spherical front, then this generalized radon transform is an invertible transformation and so on. But I mentioned, yep.
Please go ahead.
Yeah, I mentioned that this actually opens up a lot of interesting questions, and one of the questions that we are looking at is like, hey. Yeah. We can say like what type of neural networks can we use here that satisfy at least some sort of this smoothness, and we can use neural networks for performing slices.
Right.
Like that's an interesting question that we haven't looked at it, but we are currently looking into these directions as well. Yeah.
And another question is concerned with this. You see, you have a lot of sliced data, and you average it to unify it. I'm in the field. I had been in the field of computer tomography. The situation is very similar, but the averaging is not good. You must some inversion needed in the tomography. I believe, I suspect that in your case also you need some inversion of the, not averaging. Averaging is not a good strategy to unify the result?
That's another good point. I didn't talk about it here, but actually you can show that this averaging, there are certain cases that you can show that this averaging is certainly not a good idea, because in high dimensions, a lot of, you can come up with samples that a lot of your slices carry zero information for discriminating your two distributions. Okay. But then like there is a variation of this distance that's called max sliced Wasserstein distance. And instead of calculating the expected value, you calculate the supremum. You calculate the maximum, the slice that provides the maximum of Wasserstein distance. Okay. And when we went towards the end, I believe right here, yes, right here, I mentioned that we're actually optimizing over our slices as well. So here, a max sliced Wasserstein only cares for one discriminant direction. But when we are optimizing over these slices, we are asking that give us k slices, and we can also enforce like non-redundancy, essentially like some sort of orthogonality on this if we want. Right? Give us,
yeah.
Right. Give us essentially a subspace, a discriminant subspace, like provide the slicers that that discriminate the distributions the best. But so that kind of inherently becomes into play when we are optimizing over the slicers. And it's not averaging anymore.
Anyway, this is, I believe this is the future of the machine learning.
I appreciate it. Thank you so much.
Methodology, conceptual part of your talk very much. Thank you very much for this opportunity. Thank you.
Yeah, thank you very much. And yeah, thank you for the wonderful talk. And it's very, very interesting. And also thanks audience for the lots of questions. So do you have any further questions from the audience? If not, can I ask a very small questions?
Absolutely.
So you use the reference distribution, right? So actually in practice, how do you pick the reference distributions?
Okay, so yeah, I think this problem came up many times, right? So depending on which of these methods we're talking about, if you're talking about a sliced Wasserstein embedding, this reference distribution can be learned, like in a neural network, like end-to-end. But if you're talking about Wasserstein embedding, like we had before, this should be the Fréchet mean of your data set. So you would like to pick a distribution that's as close as possible to, or the Wasserstein barycenter is essentially the same idea, right? Like Wasserstein barycenter of your entire measure.
Right.
But honestly, like that calculation is going to be expensive itself. The calculation of the reference measure is going to be expensive itself. We found in practice a simple average of your data set. If your data set is registered, like there is no affine movement between these. So like if your data set is registered, like in the case of nuclei images, then Euclidean average, a simple average is also going to work really nice, right? The results that you're going to get are on par with if you use the Wasserstein barycenter as your reference.
Ah, nice. That's very clear. Thanks. Oh, actually, we have another question. Could you answer the questions?
Of the principal geodesic analysis. Yes, is this principal geodesic analysis, I believe this was a paper from Kolouri, right? Like, am I right? Maybe I'm not familiar with principal geodesic analysis. Can you elaborate? Whoever is asking, what do they mean by principal geodesic analysis? Maybe the answer is I don't know what principal geodesic analysis is. Oh yes, yes. So that's certainly it, right? So we are actually mapping the Wasserstein space to the tangent space at the reference. This is certainly true for the Wasserstein embedding and as well as Wasserstein embedding. Yes. So absolutely, yes.
Okay, so yeah, we have already passed the 1 p.m. In Japan, so maybe many people want to go to the lunch, maybe. But again, the talk is fantastic. I learned a lot. So let's thank the speaker again. And again, so we will post this seminar to the YouTube channel. So if you want to learn, check it again, please check the video in the future.